Hello everyone, welcome back. So this is yet another video from the topic carbohydrates, and in the previous videos we saw about their definitions, examples, classifications, configurations, different reactions or ways of increasing the chain length or decreasing the chain length using several organic reactions and all. So from now on we'll be looking into some examples of important carbohydrates like glucose, fructose and so on. And in this video we'll be dealing with the important carbohydrate glucose, which is a monosaccharide, and there's a lot to learn about glucose, like the various reactions or organic reactions that glucose undergo and how we came to the open chain structure of glucose, and from there we learn like reactions like the Ozazone formation, their mechanisms and all. Then we come to the cyclic structure. We learn about the two anomeric forms of glucose like the alpha form, beta form, the Mutarotation shown by them, and then we come to their cyclic structure, the Fischer projection, Haworth projection and so on. So to understand the structure of glucose, several organic reactions were carried out on glucose. So firstly, after doing several characterizations from elemental analysis and molecular mass determination and all, they came to the conclusion that scientists found out that the molecular formula of glucose is C6H12O6. It has 6 carbon atoms, 12 hydrogen atoms and 6 oxygen atoms, C6H12O6. Further, they reacted this glucose with HI. They treated it with HI in presence of red phosphorus and found that the product formed was normal hexane. So from this they concluded, from this reaction they came to the conclusion that glucose consists of 6 carbon atoms in a continuous long chain. Okay. Secondly, what they did was they treated this glucose with acetic anhydride. So when they treated with acetic anhydride, they got pentacetate. So since they got pentacetate, when we treat something with acetic anhydride, we get pentacetate when there are OH groups. Right, hydroxyl group should be there. So since they got 5 acetate units, they came to the conclusion that there are 5 hydroxyl groups in my glucose system. Okay, that was the second conclusion they came. A long chain of 6 carbon atoms, then 5 OH groups. Third thing they did was they treated glucose with hydroxylamine and they got oxime. That is one thing. Okay, hydroxylamine treatment gave rise to oxime. Another thing is they treated this with hydrogen cyanide, HCN, and they got cyanohydrin. Another thing was they oxidized this slightly. This was mild oxidation with bromine water and H2O gave rise to a monocarboxylic acid, which is gluconic acid. Okay, this was gluconic acid. So these 3 reactions, with hydroxylamine they got oxime, with hydrogen cyanide they got cyanohydrin, and glucose on mild oxidation with bromine water and H2O, they gave the product formed was a monocarboxylic acid, which is gluconic acid. And from all these 3 reactions, they came to the conclusion that there is a CHO group which is present. An aldehydic unit is present in my glucose system. Okay, because aldehydes are the ones that give oximes with hydroxylamine. And another characteristic reaction of aldehydes is cyanohydrin formation with HCN, which we already saw previously in one of the chain lengthening shortening part. We saw the same reaction, how aldehydic part reacts with HCN. In part 2 we saw that. So similarly, aldehyde reacts with HCN to form cyanohydrin, and on treatment with bromine water, mild oxidation takes place where the OH groups does not undergo any oxidation. It is only the CHO part that undergoes oxidation to give a monocarboxylic acid, gluconic acid. Okay. So they came to conclusion of the presence of CHO unit. And then what they did was they reduced this. They reduced this in catalytic reduction. They gave a catalytic reduction and they got a hexahydric alcohol, which is sorbitol. They got a hexahydric alcohol with 6 alcoholic units, which is sorbitol. So already we found that 5 OH units are there already in alcohol. From reaction with acetic anhydride, we found that there are 5 OH units. Apart from that, after reduction, we got one more OH unit. So total of 6 OH units were there, which showed that 5 of them are from this previous pentacetate thing, and other OH that came up was from the reduction of the CHO unit. This CHO unit got reduced to an OH unit. So totally we got 6 OH units. And then another reaction they did was, so from all these reactions they came to the conclusion of the CHO unit is confirmed. Another thing that is to be done, that they did was, they treated this glucose with HNO3, that is a stronger oxidizing agent. So we gave a stronger oxidation to glucose, and in that case they got a dicarboxylic acid. Mild oxidation on the other side gave monocarboxylic acid, which is gluconic acid, whereas a stronger oxidation with HNO3 gave dicarboxylic acid, which is glucaric acid. Okay, and this confirmed the presence of a primary alcohol, a CH2OH group. This confirmed the presence of a CH2OH unit other than the CHO unit. That is why we got that also gets oxidized. The CH2OH is other unit that gets oxidized to COOH on oxidation. So from all these were the different reactions, the organic reactions that were used to predict the structure of glucose. So finally the structure of glucose that was proposed is this one, which is a long chain of 6 carbon atoms. 1, 2, 3, 4, 5 and 6. 6 carbon atoms in a straight chain with 5 OH units. 1, 2, 3, 4 and 5. 5 OH units and 1 CHO unit. So this was the structure of glucose that was proposed. And if you look into the several reactions that we saw, one thing was treatment with HI giving normal hexene. Apart from that, we had treatment with acetic anhydride. Acetic anhydride is CH3COO COCH3, right? On treatment with acetic anhydride, what was the reaction that was formed? CHO was SH, we got pentacetate. So all the OH that we have get converted to OAC. H, OAC, OACH, HOAC, HOAC, and finally CH2OAC. And this was the pentacetate that we got. This was one reaction. Okay. The next reaction that we saw was the reaction of glucose with hydroxylamine. So it's like NH2OH. So what happens? It is the aldehydic part that reacts with hydroxylamine, and what we get would be CH double bond NOH. This is a characteristic reaction of aldehyde where on treatment with hydroxylamine would give rise to oxygen and CH double bond NOH. This was the third reaction we saw. And the fourth reaction that we saw was again a characteristic reaction of aldehydic groups, which is a reaction with hydrogen cyanide, HCN. So when this reacts with HCN, what happens? We get H, OH here, and a cyanide group attached to the carbon. So this an increase in the number of carbon atoms happens. So this same reaction we use for chain lengthening also, right? Okay, CHO gets converted to CHOH with an extra CN group. Another reaction that we saw was the treatment with bromine water, right? The mild oxidation with bromine water. So what happens? Bromine water can cause the oxidation of just the CHO unit. So CHO alone gets oxidized to COOH, right? And this was the gluconic acid we saw, right? That was the reaction with bromine water, the glucose, the structure. The next reaction, what did we see? we saw catalytic reduction. Catalytic reduction means what was happening with sodium amalgam. For example, if I treat with sodium amalgam, catalytic reduction happened and the CHO also got reduced to CH2OH. So finally we had sorbitol, right, which was a hexahydric alcohol. 5 OH groups we got. That was the reaction of glucose with catalytic reduction, sodium amalgam. And the final reaction that we learned was the treatment of this glucose with a strong oxidizing agent like HNO3. So on treatment with strong oxidizing agents like HNO3, what happened was both the CHO unit as well as the CH2OH unit, primary alcohol as well as this aldehyde group, both of them got oxidized. So we had a dicarboxylic acid, COOH. Here also we had COOH, and this was our glucaric acid, right. So mild oxidation, gluconic acid, strong oxidation, it was a dicarboxylic acid, glucaric acid. So these were the several reactions that we learned based on the structure, which we found out the structure of glucose to be this. And the structure of glucose is the open chain structure. Okay, it's called the open chain structure of glucose. Fine. Finally, to confirm the structure of glucose, what they did was they treated this with 5 molecules of HiO4, which is periodic acid. So when they treated the glucose, they treated with periodic acid. What they got was 1 HCHO unit plus 5 HCOOH units plus 5 HiO3 as the byproduct. Okay. On treatment with periodic acid, they got 1 HCHO and 5 HCOH, the oxidation, where we can see that this RCHO groups were on treatment with HI would give rise to HCOOH. Also, all these OH units that we have, these secondary OH groups, R2CHOH, these groups also would, on treatment with HiO4, periodic acid, would give rise to HCOOH, acids would be formed. But a primary alcohol, RCH2OH, this primary alcohol on oxidation with HiO4 would give rise to an aldehyde HCHO. So that alone gave rise to this, and all the others gave rise to this 5-HCOOH group on treatment with HiO4, thereby confirming the structure that was proposed for glucose. Okay, so now let's look into one more important chemical reaction with glucose, which is the Ozazone formation. That is, glucose, if we treat it with phenylhydrazine, I would get phenylhydrazone. Reaction with phenylhydrazine giving rise to phenylhydrazone of glucose is called the Ozazone formation reaction. So this is a glucose. I am treating with this phenylhydrazine, and what happens is the CHO unit and all gets converted, and the final product that I get is phenylhydrazone. So this is the Ozazone formation reaction. So it has a mechanism, and this is an important name reaction of glucose with glucose. So let's look into the mechanism. So what happens is, if I consider this, so this would be the thing. I have my glucose, I just wrote it in a different way. The CHO is there, then first carbon CHOH is there, the remaining 3 of them I wrote it together, and they're not needed separately, and finally CH2OH. So first, when I treat this with phenylhydrazine, C6H5NH2. So what happens is, this is a characteristic reaction of aldehyde groups. When they react with this, they form phenylhydrazone. So we'll write that. So this becomes like CH double bond N, then NH C6H5, right? And the remaining portion is there as such, CHOH, then CHOH 3 times, with the CH2OH. This is the product that we get. Now what can happen is a tautomerization. Enamine tautomerization of this happens, where this H can give off this can go off, and what the enomerization happens, tautomerization happens, and enamine is being formed, which can be written like just shorten this up a bit more. Okay, so what we get is CH, and on the other side we have NH, NH, C6H5. Then this carbon becomes double bonded OH, then CHOH 3 times, and CH2OH. Okay, right. So all this would be there as such, and then a double bond is formed between the carbon-carbon, and then the hydrogen from here has shifted to that nitrogen, so it becomes NH. The remaining is there as such. Okay, let me just write it like this. Okay, see, this is the tautomerized form of the product that we initially got on treatment of glucose with phenylhydrazine. Okay, yes, the tautomerization has happened. Now what happens is certain shifts will take place. That is, this bond would shift here, this would go back, and then this would also go back. And finally, what happens is, after all that shift, what we get is this hydrogen would go out with this portion. Along with this portion, this hydrogen also would go out as minus C6H5NH2. Okay, they are going out, and the remaining portion, what we have is carbon, hydrogen, then it's like double bond NH, then this has, after shifting, it is single bond C, this has become a ketonic group CO, and then the remaining portions we have as such CHOH 3 times, then CH2OH. Okay, all that is there as such, and this is the product we got. Finally, we are treating this with one more phenylhydrazine, that is C6H5NH2. Right. Same this phenylhydrazine, I am treating with the product that I got here, I am treating it with one more phenylhydrazine. So what happens is, the final product is CH double bond NH and NHC C6H5. Then this ketonic group also will react with phenylhydrazine. Again, characteristic reaction of carbonyl group. So this also becomes C double bond N NH C6H5, and the remaining portion is there as CHOH 3 times, and then the bottom primary alcohol CH2OH. So this, I started from here and I came to the final hydrazone. Started with hydrazine, and came to the hydrazone. Okay, this is the mechanism of ozazone formation. So now this was the structure given to glucose, the open chain structure, and it had a CH4 free aldehyde group according to the open chain structure. But if you look into several reactions that aldehydes show, like aldehydes react with sodium bisulfite to form this addition product. Okay, this is one reaction. But this reaction was not shown by aldehyde. Similarly, aldehyde groups can react with ammonia, like the same way how it reacts with hydroxylamine and all. Similarly, this aldehydes generally react with ammonia to form this imine. Double bond NH is being formed. But this reaction also was not shown by aldehyde groups. The aldehyde was not shown by glucose. Another reaction that is shown by aldehydes. That the normal in laboratories what we do for the organic analysis of functional group is the Schiff's test and the 2,4-DNP test, right? When we treat an aldehyde or a carbonyl compound with Schiff's reagent, a pink color would be formed, which indicates the presence of the carbonyl group. Or if we treat with 2,4-DNP, dinitrophenyl hydrazine, 2,4-dinitrophenyl hydrazone would be formed, which is a yellow precipitate, yellow-oranges precipitate that is formed, which we all do in our labs. But when we treated glucose with these two, either the Schiff's reagent or the 2,4-DNP, this characteristic colors precipitates were not formed. So this reaction was also not satisfied by glucose, our glucose. Also, another thing that we can look into is glucose existed in two stereoisomeric forms. One was the alpha isomer, alpha glucose. Another was the beta form, beta glucose. Glucose existed in two isomeric forms, stereoisomers, alpha and beta. So where alpha glucose was formed by what we say, we can heat a saturated solution. When we heat the saturated solution, so we will get the alpha glucose around 303 Kelvin. And above 371 Kelvin, above 371 Kelvin, from a saturated solution of glucose, we got the beta glucose. From the saturated solution, we got beta glucose. So we get two forms, alpha and beta. And this alpha has a specific rotation of around 111 degrees. And beta has a specific rotation of around 19.2 degrees. So if you talk about the specific two forms, alpha has 111 degree specific rotation, beta has 19.2 specific rotation. Now, if we dissolve them in water and allow them to stand for some time, what happens is either alpha or beta, you're putting it in, dissolving it in water and allowing it to stand for some time means they have the tendency to convert to the other form and reach an equilibrium. So alpha would slowly start getting converted to beta form and beta likewise would slowly start getting converted to alpha form and an equilibrium mixture would be formed. And in the equilibrium mixture we have alpha. Then here would be that open structure we have, our glucose, open chain glucose would be there. And similarly we have this beta form. This would be that equilibrium. Okay, so this alpha form would be some 36% and this beta form would be 64%. Alpha, which has a specific rotation of 111 degree, would slowly get converted to the beta form and be 36%, and if it is beta, that which has a specific rotation of 19.2, that also gets converted and an equilibrium of the two would be formed with 36% of alpha and 64% of beta. And at the equilibrium, the specific rotation would be 52.5 degree. At the equilibrium, it is 52.5 degrees. So alpha means its specific rotation would decrease to 52.5, slowly starts decreasing. Beta means its specific rotation slowly starts increasing and it reaches 52.5. And this is the equilibrium. And this change in specific rotation so as to from one form to from one stereoisomer to the other stereoisomer, this change in specific rotation, this is termed as we can say this could be termed as Mutarotation. It's an important property shown by glucose, Mutarotation, this change in specific rotation. So glucose, we already saw that though it has an aldehydic unit, it does not give rise to many of the reactions shown by normal aldehydes. Also, glucose exists in two forms, two stereoisomers, alpha, beta, and if you put this all, any of them in a solution and allow them to stand, they have the tendency to change their specific rotation. They will alter their specific rotation, which is called Mutarotation, and they'll come to an equilibrium state, which consists of 36% of alpha form of glucose and 64% of the beta form of glucose. So from all this, we came to the conclusion that glucose is not having a linear chain structure like this. It does not have an open chain structure. If the structure of glucose is not a open chain, then what is it? It is definitely a closed structure. How do we arrive at this closed structure? So what happens is this double bond gets shifted and this oxygen gets bonded to carbon and this hydrogen would go and bond with this oxygen. Okay. So this double bond CO, carbonyl groups, that aldehyde CO, that aldehyde no longer stays at aldehyde. It's a gamma lactone that is formed. A lactone is being formed and not an aldehyde, free aldehyde as such. So this is what happens, and two possibilities are there. One is when we have the HO written in this form, C and double bond O to the other side and H to this side. So in that case, what happens is this double bond O becomes OH, that double bond shifts and this becomes OH, and the carbon gets bonded to oxygen of this carbon atom, right? And this is the alpha form. We have alpha isomer. Similarly, what can happen is instead of this, the CHO can also exist as C double bond O and H this way. So if it comes this way, then what we get is this one. That is OH would come on this side, OH. O and H would come like this. That is this form, right? And this is the beta form. So here we have the alpha. The rest all are the same thing. That same carbon, CHO, aldehyde, free aldehyde carbon, now is getting bonded to this OH group and forming a lactone. So we have the alpha form and we have the beta form. And now this alpha and beta form, they are called anomers. The term used to refer such kind of alpha form, beta form and all, they're anomers. So what are anomers? So if you look at these two structures, you can see that they're optical isomers, yes. But they are not mirror images of each other because of just this first carbon. The first carbon alone, this is the first carbon alone, there is a change, right? H and OH, the image is not the same. There is a change in the position of H and OH groups only at the first carbon of the two, alpha and beta if I consider. First carbon alone, H and OH are in opposite direction. But apart from that, the remaining portion, everything, HOH, OH, HOH, then this bonded oxygen, CHOH, everything remains the same for both of them. All the other carbon atoms are the same except the first one. So such groups or such isomers can be called as anomers. They are not mirror images, they are optical isomers but not mirror images of each other, and there is a change in the configuration only at the first carbon atom. C1 alone has a change, so we term them as anomers. Okay. Finally, the two cyclic forms of glucose, alpha form and beta form, can be projected in another way. Apart from the cyclic chain form, we can also show it in a Howard projection form where we have a closed ring structure like this, which is the pyranose structure, right? Okay. This is the pyranose ring structure. So where do we have the ring structure in this? So if we consider the case of alpha first, see, this is first carbon. This is my first carbon, second carbon, third, fourth, fifth, and then the sixth one is my oxygen. So 5 carbon atoms and oxygen. So this I can put it in a ring form with first carbon here. 1, 2, 3, 4 and 5. And finally the sixth one is my oxygen atom that I have. Okay. Now I have to put the H and OH on this. I had my ring structure like this. And now H, and this is the pyranose ring. H and OH I'm going to add one by one like this. And everything on the left hand side, the left hand side groups would be written on top and the right hand side ones would be written at the bottom. So the first carbon atom, this is my C1 and this is my C1. It has H and OH. H on the left, OH on the right. So the left one comes on top. So H comes on top, OH comes at the bottom. Similarly, the second carbon atom, if I consider, H will be left. So top, OH is right, so bottom. Similarly, third one, OH is on the right. So OH would be written at the top, H would be written at the bottom. And for the fourth carbon, H on left, H is top, OH on right. So OH is bottom. And finally, here fifth carbon atom, this H is taken as left, which is finally this last one, this is slightly tilted, and how we have to understand this is the CH2 group comes at the top and the H comes at the bottom. So if we can actually rotate it, so in this structure, when if we rotate, we can actually see that the CH2 group is coming on the left and the H group comes on the right, and the structure is going to be like CH2 is on top, H is at the bottom. Okay, this is the alpha form because I consider the alpha one. So this is the alpha form. Now if I have to draw the beta form of this, what I have to do is, let's look into the beta form. Where does the change come? Now, to look into the beta form of this, what I have to change is, again, everything remains the same. First carbon, second carbon, third carbon, fourth carbon, fifth carbon, and oxygen. On the first carbon, where is the difference? OH is on the left, H is on the right. So what I have to do, the only change that happens in this is, this OH is on the left, so which means that my OH comes at the top and H comes at the bottom. Apart from that, for the second carbon atom, if I look, I see that H is on the right, OH is on the left. Sorry, H is on the left, OH is on the right. So it's H on top, OH on left. For the next one, OH on top, H on bottom. Then for the fourth carbon atom, H on top, OH at the bottom. And this one, since the CH2 is pointed downward, we have to tilt it, rotate it and see. So when we see it that way, we actually come to the conclusion that the CH2 will be on the left side, so it goes to the top, and the H would be at the right side, so it goes to the bottom. So all groups on the left comes at the top and all groups on the right goes to the bottom. And finally, oxygen is there. This will be the beta form. Beta form in Haber projection. Okay, so that's how from the cyclic structure we can write the Haber cyclic form of this. Okay, so that's it about glucose. I hope you understood the concepts taught in this video. So let's see you with another topic in the next video. Thank you so much.